Let's define a signal that has value from time 0 to 7. We start by defining our time variable. We're going to generate our signal with random numbers, so we initialize our random number generator so that our code is repeatable. Then we can define y as normally distributed random numbers in an array the same size as t. We will plot it in a subplot. Using circle symbols. Using the axis function, we can make sure that there is good white space around the data. So we have these 8 data points. Let's pretend that these data points are samples of a signal that is a continuous signal, like a sound wave or an electromagnetic wave. Or better yet, let's pretend that these are percent changes in the value of a stock recorded at the daily opening bell. We can label our plot accordingly. On the x-axis, we will have days recording, changes to stock value. We'll use a delta symbol to indicate change in stock. And on the y-axis, we'll have the percent change in stock value. As a first exercise, we want to use interpolation to approximate what that continuous signal might look like if we were to record it many times per day instead of just once per day. First, we define what times at which we would like to more densely approximate the signal. Our original sampling frequency was 1 sample per day. Let's try a new sampling frequency of 100 samples per day. We define our new time variable, t_interp, as ranging from 0 to 7 in step sizes of 0.01. Then, to interpolate the signal, we can use MATLAB's interp1 function, where the 1 indicates that this is the function that we use for one-dimensional signals. The arguments are the time t and signal y, where t defines the times where y takes on values, followed by the new times that we would like to approximate, which is t_interp. And finally, we specify the method, which we will choose to be the spline method in this first example. Spline interpolation uses higher order polynomial functions to perform data interpolation and is the most common form of smooth interpolation. Okay, let's see what this looks like in our plot. We do a hold on and plot it at times t_interp. We can plot this with red lines. Hey, that looks pretty neat. We see that the spline creates a continuous smooth function that passes through the data points we supplied. When we densely sample the spline function, we can, by all appearances, show what appears to be a continuous signal in our plot. We may not have had much of an idea about what the function looked like with just the 8 data points, but with the spline fitting, we see a guess at the function that makes a lot of sense. The same function can be used to extrapolate. Extrapolating future changes in the value of the stock could be very lucrative. To extrapolate, we simply need to define times that fall outside the range of the original data points. Let's extrapolate out to -2 and +2 days outside of our 0 to 10 second range. can see that this does not change what the spline does in the interpolation region, but the curve is continued into the extrapolation region. Where it goes falls outside the range of our plot. Let's redisplay it in another subplot to see where it goes. Whoa, we can see both sides drop pretty dramatically. Our prediction for 2 seconds to the left side of our data quickly heads towards some very negative numbers, approaching minus 100. And on the right, we're approaching minus 10. Maybe this is right? Who knows? But considering all of our known data points fall well within the range of minus 5 to 5, predictions that quickly go to minus 100 may be a bit rash. If we trust the prediction, it's definitely time to sell the stock because we will have a big drop in the next couple of days. This is a danger of extrapolation. The underlying polynomial that defines the spline is well behaved in the interpolation region. It connects the data with a smooth, well-behaved function, but the same function outside of the interpolation region can change dramatically. There are other functions that can be used for interpolation. In fact, there are many different flavors of splines. The spline we just saw is called a cubic spline. Another type of cubic spline is available in MATLAB called the p-chip method. We can see again in the interpolation region, this spline is smooth and reasonably well behaved and agrees with the first spline that we plotted. But again, outside of the interpolation region, it too can change dramatically. This time our prediction of future values is positive. If we are optimistic, this is a good time to buy the stock. Which prediction is right? Probably neither. Only time will tell. This is a good example of the caution one needs when extrapolating. Extrapolation is heavily influenced by the function that is fit to the data. The default behavior if no method is specified is simple linear interpolation. And with linear interpolation, the function will not even attempt to extrapolate. It simply returns a not a number value for times outside of the interpolation region, which the plot function ignores. In case we forget what we have plotted, we can now add a legend. First we plotted our data, then an interpolating spline, followed by a spline that had extrapolation, followed by a p-chip spline, followed by linear interpolation. Linear interpolation does give us a continuous function, but it's not smooth like the spline methods. Now let's look at an example where we try to recover some missing data. First, let's create an audio signal that contains 2 pure tones. We will use a sampling frequency of 44,100 Hertz. We will create an A note at 440 Hertz and an E note at 660 Hertz. Our signal duration will be 5 seconds. We define our independent time variable. And then we can define our 2 cosines. we can define our overall signal as the sum of the two cosine signals. Let's plot it and see what it looks like. We of course need to zoom in to actually see the oscillation of the waves. We can see that when we sum these two cosines, the result is no longer a cosine. That's because in some places the two waves reinforce each other, in other places they cancel. We can display the two individual waves so that we can see that this is happening. Where the peaks of the red and green waves align, the combined blue wave is highest. Where the peak of the red aligns with the trough of the green, the two waves cancel out. And in other regions, the two cosines sum to create a more complicated, non-pure cosine wave. Okay, so we have a signal. Let's simulate what happens when we lose most of our samples to data corruption. To simulate random data loss, we define a random sampling rate, R sample rate, to be 10%. We seed our random number generator. Then we randomly select the entries in our signal Y that we retain. We first generate an array of random numbers. The size of Y. And then we sort them. This creates a randomly ordered set of indices to all the entries in the Y vector. Then we can trim down this set of samples to the R sample rate fraction by keeping only that fraction of indices in the front of the index vector and throwing away the rest. We can plot the result. We display the original signal first, then we display the 10% of the samples we are keeping as red circles. We use the axis function to zoom in on 5 cycles of the signal. And we can see this is the sparse random sampling that we've obtained. Okay, now let's put our signal interpolation skills to practice. If we only have 10% of our signal samples available, can we estimate the 90% of the missing data points using spline interpolation? We create YEst for Y estimation using interp1. The data we interpolate are at times t at index, and the data are Y at index. We want to interpolate values at our original times t using spline interpolation. We can display the result in green. We can see our green spline approximation is often extremely close to the original blue signal, but sometimes there are subtle differences. And finally, how do they sound? These are audio frequency signals, so we can listen to them instead of just looking at them. First, the original. And now the spline estimation. The original signal sounds like the clean two-tone signal we expect. The estimated signal, recovered from using only 10% of the samples of the original, has the same tone as the original, but there is an unmistakable presence of noise in the background. This arises from the various new frequencies that we introduced into the signal and the imperfect approximation of the spline function fitting to the data. So we cannot recover our original signal exactly with interpolation, but we can get quite close. In the next lesson, we will see some signal noise reduction techniques.